let us talk about zeros of polynomial functions. Something we learned in the previous section was synthetic division, and as a consequence of synthetic division, which was division of a polynomial by a binomial x minus k, we arrived at the conclusion in our previous lecture that f of x could be written as g of x. Remember, a divisor is equal to, we said we were looking at the form f of x over g of x, which is in the form of a dividend over a divisor. And we can rewrite this division problem as g of x times a quotient plus a remainder. We discussed that in our previous lecture. You can view a lecture on synthetic division. Now, if the remainder is 0, we did mention that we can write any polynomial function as a divisor times a quotient. And this is what the quotient function is. All right. Well, this is going to lead to what we call our factor theorem. This is actually a theorem in this section for us. So the factor theorem is pretty simple. The factor theorem says a polynomial, call it f of x, a polynomial f of x has a factor, and that would be x minus k, has a factor x minus k, if and only if, and only if f at k is 0. In other words, there is no remainder. Okay, now let's take a look at it. It's not difficult to prove this, so let's take a look at the proof of this theorem. All right, so how is the proof going to go? Well, let's see if, let's call this proof. So for the proof, if I use division algorithm with a factor x minus k, then remember, I just have it up there too, up here, I just wrote it. Then we can write f of x as x minus k, because we are dividing by x minus k. This is our divisor instead of g of x. So we can write it like so, plus r of x. True? And then we had a remainder theorem in our previous lecture. The remainder theorem said the remainder r is the f at k. So f at k is the remainder in the synthetic division, right? So I can write this as f of x is equal to x minus k times q of x plus f at k. So instead of r of x, I put f at k. Now, qx, again, we know qx has a degree that's less than f of x, right? Quotient will always have a degree less than the dividend. So if f at k is 0, then we can write f of x as x minus k times q of x, correct? And you can see that x minus k is a factor in this case because we've written it as a product. X minus k is a factor. So that proves, that's portion of the proof. The if and only if proofs involving if and only if require proof in two directions. One is going in this direction where we simply mention that x using division algorithm that we have a factor x minus k. Now we need to go in the other direction in order to prove this one. For this going in the other direction, that's conversely speaking, for this part, for the only if portion of the proof, if x minus k is a factor, so we assume here x minus k is a factor. Going in this direction, we showed x minus k is a factor for a given condition. Now we want to show that what if x minus k is a factor? Well, if it's a factor of f of x, then the division of f of x by x minus k, what's going to happen? Well, it is a factor, right? So if we divide f of x by x minus k, what is that division going to yield, right? It's going to yield a remainder of 0. True? A remainder of 0. And so by remainder theorem, we can say that f at k is 0. And there you have it. So for going back, we're just going to show that if it's a factor, then f at k must be 0. And going forward, we show that if at k is 0, then x minus k is a factor. See how that worked? If f at k is 0, then it's a factor. Here we said if x minus k is a factor, then f at k is 0. And that completes the proof of the if and only if portion of this theorem, the factor theorem. So it's important then, if polynomial has a factor, if and only if f at k is 0. All right, now let's take a look at our next idea here. Now what I have written here is the fundamental theorem of algebra. The fundamental theorem of algebra was first proved by Carl Gauss in his doctoral thesis in about 1800. So that was really the beginning of the 19th century. And he did this when he was, if I recall correctly, he was only about 21, 22 years old. So the proof is beyond the scope of what we're doing, so we're going to state this without a proof. But the fundamental theorem of algebra is very important, and it reads, I have, if the f of x is a polynomial function, the degree is greater than 0. Remember, the 0 degree polynomial means a constant function, so anything aside from a constant function. So f of x equals 7 doesn't count. So as long as the degree is greater than 0, means linear, quadratic, and so on, then the function f has at least one complex 0. It has at least one complex 0. Now, so in other words, you can make up your own polynomials, whatever degree you want it, whatever number you want to use. Your made-up polynomial will have at least one solution. It has at least one solution, but it may be complex, not real solution. Now, using fundamental theorem of algebra and the equivalence of zeros and factors, you can obtain the next theorem, which is called the linear factorization theorem. So let me write this theorem for you. And here I have the linear factorization theorem listed for you. I will prove this theorem for you in just a few moments. The linear factorization theorem reads, if a function, a polynomial function of at least first degree polynomial function of degree n, not a constant, but at least a linear function. So suppose we have a polynomial function, then the polynomial function has precisely n linear factors. And notice here the linear factors, c1, c2, ... cn. These are complex numbers. So every solution to this function is going to be a complex solution. And remember, real numbers are subsets of complex numbers. So what's interesting about this theorem is that you have linear factors. That's why factoring is such a key skill for us in mathematics. It's important because of theorems such as this one. So very interesting. Like for instance, if I have a 7th degree polynomial, I should be able to write that as 7 linear factors in the form x minus first one, second one, all the way up to the 7th complex number. So let me actually now show you a proof of the linear factorization theorem. Okay, so here is the proof of linear factorization theorem. Now, we just talked about fundamental theorem of algebra, right? And by the way, this really interesting historic background on the fundamental theorem of algebra. The linear factorization that we're going to talk about is very closely related to fundamental theorem of algebra. In fact, that will be our starting point when I start the proof. But the fundamental theorem actually has interesting history in that in the early work with the polynomial functions, the fundamental theorem of algebra was thought to have been not true actually, because back then, many years ago, this is, I mean, we're going about 800 AD, the time of Khwarazmi, the Persian mathematician. At that time, those mathematicians did not know about complex numbers, right? So they did not think the fundamental theorem of algebra was true because imaginary solutions were not considered then. So every work with those older mathematicians did not include complex numbers, and in fact, even with Khwarazmi, negative solutions were also not considered. Now, once imaginary numbers were accepted by the common mathematical practitioners, then several mathematicians actually tried to give a general proof of the fundamental theorem of algebra, and we got some very famous mathematicians who tried it, such as Gottfried Leibniz, the father of calculus, often tagged, Leonhard Euler, the prince, the king of mathematicians, and even Lagrange and Laplace. They all tried to prove this theorem, the fundamental theorem, but they weren't successful at it. The correct proof of the fundamental theorem of algebra is credited to truly Carl Gauss, again, who published it in his doctoral thesis. So very interesting historical background. Let's actually proceed to our proof of this linear factorization theorem. Now, according to the fundamental theorem of algebra, right, we know that the function must have at least one complex zero, right? So I can write f of x, any polynomial function, in the form of x minus a linear factor, or if I'm allowed to have complex solutions, right, times a quotient. That would be f1, f sub 1 of x, right? Now, if the degree of this f1, f sub 1 of x is greater than 0, then that means I can apply the fundamental theorem of algebra again, right? So the second iteration, I'm going to break this, in other words, itself. Think of that as a function, as x minus its own factor times another polynomial function, right? Another quotient. If the degree of f sub 2 of x is greater than 1, then we can further break it into another linear factor. See how that works? X minus c3 times f sub 3 of x, and so on and so forth. So it's clear that the degree of f sub 1 of x is n minus 1, right? Fx degree is n, right? And because we're dividing by a linear factor, therefore the degree of the first polynomial is going to be n minus 1. This is going to be n minus 2, and so forth, right? And you can repeatedly apply the fundamental theorem of algebra n times until we obtain what we are after. So you see, the proof is really simple. Not the proof of fundamental theorem of algebra, but the proof of linear factorization theorem. So you do this over and over n times until you eventually get down to a linear factor. Okay, and at that point, you've built up to that nth degree polynomial. So all we got to do is now actually attach the general constant leading coefficient. So therefore, we can write this as a sub n, x minus c1, x minus c2, all the way up to x minus c sub n. And again, a sub n is the leading coefficient. We allow it to be different from 1. Okay, that part of it I could have started by let's say writing a sub n here, so that doesn't break the proof of this theorem. And there you have this one. Okay, the other note I want to make is that the following, that the fundamental theorem of algebra and the linear factorization theorem that I just went through, they only tell you the zeros or factors of polynomial exist. That's all they say. They say exist, now go find them. But they don't show you how to find them, correct? They just tell you, yeah, they're there and you should be able to do it. But they don't tell us details on how to do it, how to find these zeros. So for that reason, theorems that are typically stated like this, without showing you how to do it, they call these existence theorems. So both of these theorems are existence theorems. Now, the other takeaway from the linear factorization theorem, therefore, is that the number of zeros theorem, let me put that one here also, the number of zeros theorem. And this one's going to be pretty simple. Let's say a function, let me just call it a polynomial function. That's all we're doing. A polynomial function f of x, okay, of nth degree, or degree n of nth degree, has at most, meaning no more than, at most n distinct zeros. And that's perfect because now we have a bound, an upper bound on number of zeros of a polynomial function, right? A fifth degree polynomial can have no more than 5 solutions. So that's good. That means polynomial nth degree have finite number of solutions limited by the degree of the polynomial. So that's great information for us. Next, let's talk about the rational zero theorem. So I'm going to put that theorem for you first. And here it is, the rational zero theorem. Now, the key word, by the way, folks, in this theorem is the word rational. Remember, rational numbers are numbers that are written in the form of p over q, where p and q are integers, right? So your numbers such as 2/3, 5, 1/7, and so on, these are all rational. Numbers that are not rational become irrational. So for example, pi, square root of 2, and so on. These are not included. So this theorem only applies to rational numbers, rational zero theorem. It's a pretty interesting theorem. The theorem reads, if a polynomial function has integer coefficients, that's also important, not fractions, but integer coefficients, then every rational zero, again the emphasis is on rational, not irrational. Rational zero, the function, is in the form of the rational zero is of the form p over q. Now what are p and q here? Where p and q have no common factors, by the way, other than 1, and p is a factor of the constant term. So p is a factor of the constant, and q is a factor of the leading coefficient a sub n. All right, so that's what we have again. Again, p here, factors of the constant, and q here is a factor of the leading coefficient. All right, now this is one of the few theorems that actually helps us finding the zeros. Not the fundamental theorem didn't help us. They just tell us, yeah, they're there, go find them. So once you form this list of possible rational zeros, which is going to be sometimes a long list, because you're going to list all factors, right? Remember what p and q are. P are factors. So for example, if a number is 10, we got to write factors of 10. Those are plus minus 1, plus minus 1 times 10, 2 times 5, and all the plus minus possibilities, right? So once you list these possible rational zeros, then what we do is we use trial and error method to determine which, if any of those, are actual zeros of the polynomial. And again, you got to note that when the leading coefficient is 1, the possible rational zeros become just the constant term. When the leading term is 1, that means, I'll show you. When this is 1, because the factors of 1 are just 1. So then the rational zeros become factors of the constant term. Okay, so let's see if we can work this one. Okay, we're going to show this theorem without the proof, by the way. So let's find the rational zeros. I'll make up a polynomial and we'll take a look at it. to try this theorem. So in our example, suppose my function is f of x, x to the fourth, negative x cubed, plus x squared, negative 3x minus 6. So a simple polynomial here, right? And we want to find the rational zeros of this one. So because the leading coefficient, this coefficient is 1, let me just write down a sub n is 1. A sub 0, the constant, is negative 6, right? P, factors of leading coefficient, plus minus 1. And Q are the factors of, what you call it, the factors of, oh, actually P are the way I have it, factors of constants. Hold on, those are factors of 6, negative 6. That's plus minus 2, plus minus 3, plus minus 6. Q is a factor of the leading coefficient, and that's just plus minus 1. Now, why is it plus minus? So for example, this 1, I can write 1 as product of 1 times 1, or I can write it as negative 1 times negative 1, right? That's why the factors of 1, we look at both positive and negative factors. What about negative 6? For example, negative 2 times 3 is negative 6. 2 times negative 3 is also negative 6. So we pick up both plus minus 2, plus minus 3 for that reason. Okay, so that's why we have this plus minuses all of a sudden. Now, let's, again, when I do a ratio of P to Q, so I'm going to go plus minus 1, plus minus 2, plus minus 3, plus minus 6, dividing it by plus minus 1, right? Those are factors of Q. So you divide individually, and this will give me, well, plus minus 1 divided by 1 is itself, right? Plus minus 2 divided by 1, it's going to be plus minus 2. Same thing with 3, same thing with 6. So that's what I said earlier. If the leading coefficient is 1, then you only look at factors of the constant. Your rational zeros are only factors of the constant term. Now, if this function has a rational zero, and no guarantee that it will, but if it does, it's got to be one of these. It's not going to be outside of these. It's not going to be 7. It's not going to be 2/3, 1/2, and so on. So let me try 1, for example. This is the trial and error segment of our work, right? So I'm just going to repeat the polynomial function. The leading coefficients are 1, negative 3, 1, negative 3, negative 6, right? These are the coefficient on f of x, the polynomial. Now we can do our synthetic division. Bring down the 1 times on 1, minus 2, multiply, add, multiply, add, multiply, add, and what we're looking for here, by the way, is 0. This is not 0. Why 0? Because if it's 0, remember by factor theorem, if the remainder is 0, then that means we have a solution, right? We have a solution to the equation. So this isn't 0. That means 1 is not a 0 of the function. Let's try negative 1. And that's the trial and error portion of our work. 1, negative 3, 1, negative 3, negative 6. This time, bring down the 1, multiply, add, multiply, add, multiply, add, negative 8, multiply, add, we get 2. Make sure I, hold on, the polynomial, hold on, I didn't, no, so sorry, I messed this one up. The coefficient are 1, negative 1, 1, negative 3, 1, negative 1, 1, negative 3. Yeah, sorry, I messed that one up. Let's try 1 again. So sorry about that. Let me bring down the 1. The 1 times 1 is 1, 0, 0, 1. 1 times 1, 1. Subtract, multiply, 1 minus 2, bring it here. That's negative 8. Okay, so 1 doesn't work. Still, it doesn't work, but for a different reason. Now, let's try negative 1, only I'm going to do it correctly with the correct coefficients. The coefficients are 1, negative 1, 1, negative 3, negative 6. Make sure I copy them correctly. Okay, let's try this. Bring down the 1, multiply, add, multiply, add, multiply, add, multiply. There, I did that one right. Add. And there we have it. A remainder of 0. So that means negative 1 is a solution. So this is what we know so far. That f of x can be written as x minus c times a quotient. Now we started with a 4th degree polynomial, so the degree of quotient is a 3rd degree. So far is x cubed negative 2x squared plus 3x minus 6. Right? We were able to factor it like that. So we have one solution, x is 1. All right, now let me try 2. And what we can do is now we can think of this quotient, this one, as a new polynomial. Write its coefficients. And the same rational zeros in the previous list, these still work, right? Because those are the rational zeros of the original polynomial. So they should still work with this new polynomial. Or you can create your own P over Q again, but it's redundant. I would not advise to do that. And this time I'm going to try, let's try 2. I tried 1, didn't work. Let's try 2. Hopefully it works. Bring down the 1, multiply, 0 times, multiply. Perfect. We got another 0 of this polynomial. So x equal 2 is also a 0. The factored form so far, f of x is x plus 1. I'm sorry, we found x to be negative 1 here. I said it, see right in here. I just didn't copy it correctly. Got to be careful. So x plus 1, and this time is 2 is a solution, so it's x minus the 0, x minus the solution, which is that, times this quadratic now is going to be, this polynomial is going to be quadratic. The degree of the quotient will be 1 less than the degree of the polynomial we just divided it by. Or it was, yeah, divided. So that's going to be x squared plus 3. And usually once we're down to the quadratic, we just use quadratic formula or try to factor it. Well, here I have x squared plus 3, and I know if I said x squared plus 3 equals 0, x squared is negative 3, and we can square root both sides. And we have a couple of imaginary roots, right? The roots are root 3i. And there we have it. These are the imaginary solutions. So if you're looking for real solutions, if you're looking for rational zeros, let me just, since we talked about rational zeros, the only rational zeros were negative 1 and 2. These are not rational, right? The root 3i, that's irrational. But nonetheless, there are solutions. So if you want all 4 of them, there you go. We got to count those solutions as well. All right, so that takes care of the rational zeros. And I think the only thing that remains for this section that we got to talk about is the actually a couple of ideas still. One is the conjugate zero theorem. Let me put that theorem for you, the conjugate pair theorem. All right, so I have this conjugate zero theorem written down for you. It's actually good because the previous example I did is still up there. Notice that we have 2 complex solutions. One was root 3i, the other one is negative root 3i. These 2 complex numbers are said to be conjugates of each other. So what is a conjugate of a complex number? If a plus bi is a complex number, its conjugate is a minus bi, and vice versa. So these are conjugate of each other. So for instance, 2 plus 3i, its conjugate is 2 minus 3i. Conjugate of 2 minus 3i is 2 plus 3i. So these are just complex conjugates. Now, the theorem goes like this. Suppose we have a polynomial function that has real coefficients. Remember, the key is that the coefficients on these terms must be real. If the coefficients are complex, this theorem doesn't necessarily work. Okay? And the proof of it is actually not that complicated, but I'll forego the proof of this one. If a plus bi, or b can't be 0. In other words, if b is 0, then I don't have a true complex number. If a plus bi is 0, the polynomial, then the conjugate a minus bi is also a 0 of this polynomial. Okay, so in other words, complex solutions occur in pairs. Keep that in mind. Complex solutions occur in pairs. So we're going to take a look at an example here. So in this example, so let's say I have a polynomial. Let's say I want to find a polynomial. How's that? Given zeros, let's find the polynomial. So we want to find f of x, polynomial f of x I'm going to go least degree, and I'll explain why I need to have that, of least degree. Okay. Having only real coefficients. So in other words, I can use the conjugate pair theorem. And let's create a couple of zeros. Okay, and as zeros, let's make one of them real, the other one, I'm going to make it 2 plus I. All right, so we want to find the polynomial of least degree. And again, I'll clarify what do we mean by least degree here in a moment. So how is this going to go? Well, in factored form, the polynomial is going to be x minus 3 because 3 is a 0. Remember, the linear factorization theorem was x minus c1, c2, and so forth, x minus c on. We can c sub n, we can write polynomials as product of linear factors, where c's are zeros here. So here's one 0. The other 0 is x minus 2 plus I. Now, by complex conjugate theorem, because we have real coefficients, because this polynomial will have real coefficients, then I know the other 0 of this polynomial is going to be x minus, the conjugate of 2 plus I is 2 negative I. Okay, now here's x minus 3, and then you can remove parentheses from inside the first group. That's going to be x minus 2 minus I. The removal of parentheses inside will be negative 2 plus I. Okay, and then you can multiply these. We can FOIL them. I'm going to let you do that part, see if you can do that. And I'm just going to put the result of the multiplication. Okay, you can verify that. Remember, I squared is negative 1. So, for example, here when I multiply I and I get I squared, replace it by negative 1. So I did, and this is what I got. I got x squared, negative 4x plus 5. And then distribute this over, and I get x cubed negative 7x squared plus 17x minus 15. So here's my polynomial with real coefficients. Now, this is a third degree polynomial. So this is the polynomial of at least degree that has these solutions. So now if you look at another f of x that works, would be this one. If it's x minus 3 squared, for example, see, it has the same 0, right? It's just repeated. And then if I go x minus 2 plus I, x minus 2 minus I, the conjugates, this 2 will work. This will work as well. But what's the degree of this polynomial? Its degree is going to be, well, it's a second degree from the first factor, and xx plus second degree. So this is going to be fourth degree. So that's not the least, right, of the least degree. And if I want, I can change this to x minus 3 to the 7th power. And check this out, x minus one root is 2 plus I times the other root conjugate minus 2I, make that cubed. Again, 3 makes this 0, so 3 to the 7th power is 0. And these roots make these factors 0. The complex solutions will make this factor 0, and so on. What's the degree of this polynomial, where x times x is x squared? And then you cube it, so this is 6th degree. This is 7th degree. I'm looking at just the leading term here. So x to the 7 plus 6, this is a 13th degree polynomial. And it works. It will have exactly same zeros as the one that was the least degree, the solution that we have. This is the solution. But that's why we want the least degree. We don't want these higher degree polynomials, because you can make it as large as you want. And that's not what we really want to do with these. Okay. Now, when it comes to zeros of polynomial functions, okay, so we can actually, this conjugate pair theorem of zeros can help us predict the number of real zeros of polynomial functions with real coefficients. Okay, so if a polynomial function with real coefficient, so if f of x has odd degree, like 3rd degree, for example, the one we just did, has odd degree, call it n, and let's say it has to be at least a linear factor, okay? Then this polynomial function must have at least one real zero. This must have at least one real zero. Why is that true? Well, suppose I have, just like this one, if I have a 3rd degree polynomial with real coefficients, well, we know it has at least one complex solution, right? And because zeros of the forms a plus bi occurs in conjugate. Now we're saying it has at least one, means it could have one or 2 or 3, but it has at least one. Because again, an nth degree polynomial has precisely n zeros. So again, a 3rd degree polynomial, for instance, I'm just making something off the cuff, x cubed plus 2x plus 11. This is an odd degree polynomial. It has at least one real zero. It could have 1, 2, or all 3. But because complex conjugates occur in pair, this is 3rd degree. So if a plus bi is a solution and I don't know, well, a minus bi must be also. That accounts for 2 zeros. There's still 1 0 at large, right? So that 3rd one must be real. And that is what this statement is saying. It has at least one real zero. It could have 1 or 3. And it couldn't be 1 or 2 real zeros, right? So for example, I couldn't have a polynomial, for instance, again, I'm making something off the cuff, minus 2x plus 8, 17. If this has 2 real zeros, suppose it has 2 real zeros. Well, what about the 3rd one? Can the third one is complex? Can it be? It can't, because we just said if the coefficients are real, the complex roots occur in pairs. So that 3rd one cannot be complex, because if this is a solution, we just said that a minus bi has to also be a solution. So odd degree has at least 1, as many as 3 for the 3rd degree in this case. And what about if it has even degrees, right? So if f of x has even degree n, and this time, again, n must be at least 2, right? Because it's even degree. And then this one may have, this is opposite of the one that's above. This one may have no real zeros. You see that? And the reason is, for example, let me make one up. F of x is x to the 4th plus 3x squared plus 7. There you go. This one, I see that this may have complex roots. Now, here's the reason. Because complex solutions occur in pairs, right? So it is possible that all 4 of these could be complex, right? 2 pairs, for example, it could be 1 plus minus 2i. The other one would be 3 plus minus 4i, because they appear in pair, right? So they could consume all 4th degree here. So it is possible that this may have no real solution. Good example is this one, x squared plus 4. This one has no real solution. If I solve this, square root of negative 4 plus minus, see, they appear in pair, 2i. So this is what this is saying. If it has a degree greater than or equal to 2, then it may have no real zeros. May have it, may not. So that's what these are. And the last thing we want to talk about is the Cortese rule of sine. Now, the Cortese rule of sine, I'm just going to copy this piece for you because it's kind of lengthy. Okay, let me do that. Actually, let me before I actually copy this, the Cortese rule of sine for you, let me talk about something that's used in the description of the Cortese rule of sine, and that is the variation in sine. Variation in sine of a function. So what do we mean by that? Let's say I'm just making something up here. Okay, x to the 7 plus x6 minus 3x fifth minus 4x4 plus 2x cubed minus 5x plus 11. Something totally made up. Now, as I move from left to right, from term to term, notice the first term is positive. Positive, second term positive. So they're both positive. As we go from x to the 6th to x to the 5th, we go from positive to negative, right? So there's one variation in sign. It varies, it changes. As you go from x to the 5th to x to negative x fourth, sign negative stays negative. So that is not a variation in sign. You go from 4th degree to 3rd degree term, there is a variation in sign from negative to positive. And then as you go from x cubed to negative 5x, there is a variation in sign. From negative 5x to 11, another variation in sign. So this function has 4 variations in sign of f of x. Okay, now let's do f of negative x. I'm going to change x with negative x. Plus negative x to the 6th, negative 3, negative x to the 5th, negative x to the 4th, plus 2, negative x quantity cubed, negative 5, negative x plus 11. Now, negative x to the 7th is negative x7. Negative x to the 6th remains positive. Negative x to the 5th becomes negative x to the 5th times negative 3 makes positive 3x 5th. The next one, negative x to the 4th is positive. A negative in front of 4 makes that a negative 4x 4th. Next one would be negative 2x cubed. Next one, positive 5x plus 11. Okay, now let's take a look at variation in signs of f of negative x. We start with negative term to positive. There's one variation. Then it doesn't change. There's one variation from the 5th to 4th degree. Then it doesn't change. Next one doesn't change. Here it changes from negative to positive and stays positive. So notice there are 3 variations in sign of f of x now. All right. So this is what we mean by variation in signs. Now I can paste. There you go. And this is what the Cortese named after René Descartes, the Cortese rule of sine. Okay, f of x is a polynomial function with real coefficients. Again, this is important, folks. Got to be real coefficient. And a non-zero constant term. If the constant term is 0, then that means we can factor the polynomial, right? X cubed plus x squared plus x. The constant term is 0, so I can factor this. Now this is non-zero. You see that? So that's the reason for being non-zero constant. Okay. With terms in descending powers of x, exactly like I have it in my previous example. Descending powers. So it goes 7, 6, 5, 4, like that. Those are descending powers of x. All right. So suppose we have this polynomial. The number of positive real zeros of the function is equal to the number of variation in sine in the coefficients of f of x, or is less than that by a positive even integer. And then this is the number of positive real zeros. The number of negative real zeros, we look at the variation in sines of f of negative x. It's either that, whatever the variation in sine is for f of negative x, or less than that by a positive even integer. Both of these. So what the Cortese rule of sine does not do for us, it doesn't help us find them again. It's one of those things that it says, well, this is what you could expect. Now, whether it happens or not remains to be seen. But you could have 4 positive real zero, you could have 2, or you could have none. I'm not sure if that's going to help us or not, but let's try this one. Okay, let's try it. So with an example. So suppose my function, we'll make it simple. X to the 4th negative 6x cubed plus 8x squared plus 2x minus 1. So let's take a look at variation in sines. Okay, here's one variation in sine. From here to here, that's 2. Then it doesn't change. The next variation in sine, see, plus to minus, that's the third one. So it has 3 variation in sines, right? So I'm going to form a table here. Put P for positive, N for negative, and then I'm going to put C for complex solutions. Okay. Now this is a fourth degree polynomial. So I would expect to have at most 4 solutions, right? Now, the variation in sine for positive, it's 3. So in other words, this one could have 3 positive. Because it's a 4th degree, it means the other one should be negative. And there's no complex, because the 3 and 4 exhausts the degree. That's all 4 degree that we need. So that's the maximum possible, and we've exhausted that. So there's no chance it will have a complex. My funny looking C here is these are complex solutions. Complex solutions. That's what these are. Okay. Or less than this by n is positive, is a variation in sine, or less than the number variation by a positive integer. So it could be 3 or 1. Well, if it's 1, and this is a 4th degree polynomial, right? If it's 1, that means how many negatives could I have? Right? I could have 1 negative, right? And, or hold on, 1, or I could have 3 negatives and no complex, because this is a 4th degree polynomial, right? Now, let's look at variation in sines of f of negative x. F of negative x becomes negative x to the 4th, negative 6 times negative x cubed, 8 times negative x squared, plus 2 times negative x minus 1. This becomes x to the 4th plus 6x cubed plus 8x, because negative x squared is positive, minus 2x minus 1. Look at the variation in signs. No, 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 no. There's one variation in sign and nothing. So there's only one variation in sign from here to here. So that means it can only have one. According to this, it can only have one negative, right? So I'm going to cross this out. Interesting. See, based on going positive, this is what just the positive variation in f of x said. At that point, I had not done variation in sign for f of negative x. Now we have new information. So because we have new information, and this one now can only have one negative. So if it has one negative, remember the degree is 4. 4 is the total number of solutions. That means the other two must be complex. So that's the only possibility. Now, variation in sign of f of negative x is 1 or less than that by a positive integer. Well, if it only has 1 less than this by a positive integer, 1 minus 2 is negative 1. Doesn't make sense. I cannot have a negative number of solutions. So if it was 2, the next one less than that would be 0. It means no negative solutions. And there you have it. Again, this doesn't tell you how to find it. It just tells you how many potentially there could be. Okay. And and that is it as far as the lecture goes. Now let me do some exercises for you. This is a long section. It has a lot of good information on it, folks. A very key section at that. It's one of the most important sections of college algebra. So this lecture is probably going to be run for about an hour and 20 minutes long, just to forewarn you. Remember, if the lectures are too long, don't watch the whole thing. Just pause it, take a break, come back and watch it again. So let's take a look at some examples here. So in this example, let's say I have negative 2x to the fourth. It's going to be a polynomial function with real coefficients. Let's say 8x squared. Let's make this negative 3x minus 1. Or 13, minus 13. And here, I'm going to use x plus 1. Okay, and we want to use the factor theorem and synthetic division to see whether the x plus 1 is a factor of this polynomial. So is this a factor? That's what we want to know. Is that a factor? So let's do synthetic division. Negative 2, negative 5, 8, negative 3, negative 13. Remember, we list all the coefficients. If a term is missing, you put 0 as a placeholder for that position. Now, and the form is x minus k. So in this example, k is negative 1 because I have x minus negative 1. That's how you get x plus 1. So I'm going to put negative 1 here. Bring down negative 2 and proceed with synthetic division. Multiply, put the number here and add. That's first step. Then we're going to multiply and then put the product here and add. So let's do this now. We'll make it go faster. Multiply, add, multiply, and add. The remainder is 1. So the answer is no. X plus 1, not a factor, because if it was a factor, remember the factor theorem, if the remainder at k is 0, then x minus k is a factor. So this one, unfortunately, is not a factor. All right, so that's pretty easy. Now let's do one where we have to break this polynomial with real coefficients into linear factors. Okay, so suppose my f of x is 6x cubed plus 13x squared negative 14x plus 3. Okay, and let's say let's say this one is a 0. Okay. So suppose I know that's a 0, and we want to find the other linear factors. We're going to do synthetic division, right? 6, 13, negative 14, and 3. We're going to put negative 3 here. In other words, x plus 3 is a factor. Bring down the 6, multiply, add, multiply, add, multiply, add, 0. So yes, f of x right now is written as product of a factor x plus 3 times 6x squared, negative 5x plus 1. Remember, these are the coefficients on the quotient. Because this was x cubed, the degree of this term starting with 6 is going to be 1 less than that, which makes it 6x squared. And once we're down to a quadratic, usually we try to factor the quadratic. So let me try to factor this maybe by trial and error. Okay, so I'm going to go 3x, 2x. That's how I'm looking at this polynomial. And let me go minus 1. So that's going to be negative 3x, negative 2x. Yep, that's going to work it. Perfect. So the factored form is x plus 3, 3x minus 1, and 2x minus 1. Linear factors. And the solutions, of course, the solutions, might as well write them. Solutions, x is negative 3. What makes 3x minus 1, 0? Add 1 divided by 3. So 1/3 is the other 0, and 1/2 for the last binomial factor. So we managed to write it in factored form as well as get all 3 solutions. Notice third degree, it has exactly 3 solutions. And all of them were real, no complex solutions on this one. Okay. Now let's do one where we have a complex 0 just to see how this works. So suppose I have f of x is equal to, again, I'm going to go with a third degree. X cubed negative 7x squared plus 17x minus 15. And suppose we know a 0 is 2 minus I. By complex conjugate theorem, 2 plus I has to be the other one. Correct? Therefore, x minus 2 minus I is a factor, and so is x minus 2 plus I is a factor. All right, and we can multiply these out. So that's going to be x minus 2 plus I and times x minus 2 minus I. And we can, let's see, we can get the other factor. Once I have this one, we do a long division. Okay. So let me multiply this, combine like terms so the video doesn't get to be too long, and I'll show you the answer to the product, to this product here. All right, so I did multiply it, and this is what I got. Now, remember, this is a third degree. I have 2 complex conjugate zeros. I have 1 more 0 remaining, and I know that other 0 cannot be complex because if it too is complex, it has to appear in pairs, right? But these are real coefficients, right? And that can't happen. So in search of the only real solution, I'm hoping it's rational, so I can do my rational 0 test. P, the coefficient on the constant, this one, all factors of the constant, not the coefficient, factors of the constant. That's plus minus 1, plus minus 3, plus minus 5, plus minus 15. These are factors of 15. Like 1 by 15, 3 by 15, you know, plus minus gives you the 15. Q are the factors of the leading coefficient, plus minus 1, because that's what that is, just 1. So P over Q, therefore, is going to be, we divide every one of these by 1, you get all of them back the way they were. So I get plus minus 1, plus minus 3, plus minus 5, plus minus 15. Okay, so remember, trial and error. I'm going to guess 3. Okay, 3. You can try 1, -1, 3, -3. I'm going to go with 3. Do a synthetic division of the polynomial by 3. And let's see what happens. Bring the 1 down. 3 times 1, 3. Subtract. Multiply, add, and there you go. No remainder. So 3 is a 0. Therefore, I can write my function. I can write f of x as a linear factor, x minus 3 times x squared minus 4x plus 1. And notice this should be the same thing here. Let me make sure I did this correctly. I see. Okay, right in here, this number, let's see, I got -4 I, and negative I is negative I squared 1. Negative times negative 2 is positive 4, and 1, that's a 5. Sorry. So that's where my error was. When I multiply -2 times -2, that's 4. When you do I, negative I, you get negative I squared, which is 1, and those two make up a 5. Now it looks better. Okay, perfect. So we were able to find the other zeros, in other words. Okay. So the zeros are, let me say, just to finalize, zeros are 3 and 2 plus minus I. Those are the zeros of this one. All right. Now, let's see. Let's say we want to find the zeros of something that has higher multiplicity. So suppose f of x is x minus 2, and then this is cubed x squared minus 7. So the 0, one of them is x minus 2 is 0, so x is 2. Because the degree is 3, therefore we're going to say that 2 is a 0 of multiplicity 3. 2m equal 3. Multiplicity is 3. The other zeros, x squared minus 7 is 0, x squared is equal to 7, x is plus minus root 7. So the other zeros are plus or minus root 7. And there we have that one. Okay. Now, let's say, let's do another one. So how about this one? Suppose I want to find now. The question is find f of x, a polynomial, third degree. Third degree. And suppose, and we want them real coefficients, okay, with real coefficients. And the zeros, let's make him 0 itself is a 0, and a 0 of 1, multiplicity of 2. And suppose I want also f at 2, the value of the function when x is 2, to be 10, something like that. So how are we going to do this one? F of x is going to be a sub n times x minus, again, I'm going to go c1, x minus c2, x minus c3, because this is third degree. So the linear factorization will look at 3 factors. Now a sub n is to be determined. That's why I need this information to find a sub n in the end. X minus zeros. The zeros are 0 itself and 1 with multiplicity of 2. So I have x minus 1, x minus 1. So what will this give me? This will give me, well, x minus 0, that's just x. And x minus 1 squared, because that's what these two are, is x squared, negative 2x plus 1, right? We can FOIL it and see what the FOIL method gives you. That's x squared minus 2x plus 1. And I can now distribute. So here's a sub n. It's going to be x cubed, right? Negative 2x squared plus x. All right, so that's the polynomial. Now we have a condition. F at 2 should be 10. So plug 2 for x. I get a sub n. 2 cubed, negative 2 times 2 squared plus 2. And f at 2 must be 10. So left side is 10. The right side is 2 cubed minus 2 cubed is 0. So I have 2a sub n. Therefore, the leading coefficient is 10 halves or 5. And that should do it for us, right? So I can say that the polynomial f of x is 5 times x cubed negative 2x squared plus x. Where am I looking at? I'm looking at this form right here. The one that that's complete polynomial form. And then distribute the 5 over to every term. So I get 5x cubed negative 10x squared plus 5x. And that will be the polynomial, the final form of that polynomial with those specifications. Okay. Now, let's take a look at another one. For this next example, suppose, again, I want to find the polynomial of least degree with real coefficient. This time, let's make it the zeros that are irrational. 1 plus root 2 and 1 minus root 2. Okay, and 1. Suppose I have that polynomial of least degree with these zeros. Okay, now the least degree, because I have 3 zeros, is going to be a third degree, right? A third degree. Therefore, f of x is going to be, and the coefficient, I'm going to take a sub n to be 1, because really the coefficient doesn't affect the zeros. And one root is going to be x minus a 0, then x minus the other root, x minus the other root. Okay, and we have those. Now, I can distribute. Let's distribute. So this is going to be, well, remove parentheses first. So it's going to be x minus 1 minus root 2, x minus 1 plus root 2. And we'll keep x minus 1 outside. I'm going to actually multiply these together. And this time I'll show you the details of the work that I'm doing. Okay. So this becomes, and I'm distributing this way, and then this way, and then this way. Okay. And you can try to see if you can do that on your own also. X times x, so that will be, first term is going to be x squared minus x plus root 2x. Distribute negative 1, so I get negative x plus 1 minus root 2. Notice how I'm doing this in columns, right? I'm doing it in columns. Did that distribution. Now the next one is negative root 2 times x is negative root 2x. Negative root 2 times negative 1 is positive root 2. Negative root 2 times root 2 is negative square root of 4, which is just 2. So there we have that one. Now I can add these in columns. I get x squared. These are opposites. Negative 2x minus 1. So that's when you multiply these two expressions. Therefore, my f of x is going to be, so I'm just going to say it's all of that, and then remember it's times x minus 1. Therefore, f of x will equal to x squared negative 2x minus 1 times x minus 1. Okay, and then we can distribute, combine like terms. That will be x cubed negative 2x squared positive 2x. I'm distributing from the right. Okay, and do negative 1 times x squared. That's negative x squared plus 2x plus 1. Combine like terms. X cubed negative 3x squared plus 4x plus 1. And that would be the polynomial that we're looking for. There you go. Having those zeros as intended. Okay. And again, making sure I got my x terms correctly here. Let me just check real quick here, folks. Let me get right in here. Actually, look like I did when I distribute it. Got x cubed negative 2x squared. This should be negative x, not 2x, right? So let me correct this one. That's negative x. And then this distribution gave me negative x squared plus 2x plus 1. Yeah, that one looks good. Good thing I checked. So, it should be okay now. X cubed, negative 3x squared. This should be plus, hold on, my pen is acting here. Hold on. Okay, got it. Plus x plus 1. There we go. Those are like terms, and plus, that should be right. I just checked up here. Everything up here looks good. And there you go. That should be the correct answer. You could factor it, use rational zero theorem, and then make sure that this works. It should work. Okay, so got that one down. Now, let's do another one. This time we want to find all zeros, and the solution, let's allow for complex solutions. Okay, so let's say we could have possibly complex solutions. So f of x this time is going to be x to the 4th plus x cubed. Notice I did not use the Cortese rule of sine here, right? Because it really doesn't help us much in the way of solving. It just tells you the expectation of what you could expect. All right, now when we were given something like this, the very first thing we do, we want to find the rational zeros. So remember, p, and this would be the coefficient, all the factors of the constant. Factors of 4 are 1 by 4, 2 by 2. And the factor of q is a constant plus minus 1. The constant, the coefficient in front of x to the 4th, not the constant. The coefficient in front of x to the 4th. Therefore, p over q, because you're going to divide everything by 1, you just get all factors of p. Plus minus 2, plus minus 4. All right, and we have that. Now, synthetic division by, let's try, usually we try just like 1 and negative 1, and hopefully they work. If not, we go to higher numbers. The coefficients on the polynomial 1, 1, negative 9, 11, negative 4. And let's try 1. Bring down the 1, multiply, add, negative 7, multiply, add, multiply. Yes, it worked. Perfect. So that one is good. It worked. So we do have a 0 at this point. Okay, so we do have a 0. So far, the rational 0, x equal 1. Now, because this is a 4th degree, again, it is possible, by the way, to have zeros that repeat. That's why we get higher multiplicity. So, for example, could 1 be the solution again? Let's try 1. It could be. Bring down this 1. 1 times 1 is 2. We multiply and then move it here and then add. Now, when I do that, let's see, 1 times 3, 3, minus 7, negative 4, and there, sure enough, there you go, you see that? So it is possible for a 0 to repeat itself. With higher degrees, very likely this could happen. So far I have x is equal to 1, and this one has multiplicity of 2. Now, would 1 work again? It could. Let me try 1 again. Probably won't, but it might. 1 times 1 is 1. Oh, look at that. 1 works again. So multiplicity is 3 now. Will it work again? 1 and 4, 5. No, not 0. Okay. So we have a 1 with multiplicity of 3. That's remarkable. Perfect. Now, at this point, by the way, this is just a linear equation, right? X minus x plus 4 equals 0, so x is negative 4. And there's one of the other rational zeros in our rational zero list. No need to do synthetic division. Once we're down to linear quadratic factors, we usually use factoring, or in this case, it was a linear factor. We just solve it. So the other solution is going to be negative 4, and we found all solutions. Again, because this is a fourth degree, it can have at most 4 solutions, and we found all 4 of them. No complex solutions in this one. No complex solutions. So let's try another one. Okay, let's look at our next example. F of x this time is 2x to the fourth negative x cubed plus 7x squared negative 4x minus 4. Again, our rational zeros, p coefficients of the constant, plus minus 1, plus minus 2, plus minus 4. Q are coefficients of the leading term, plus minus 1, plus minus 2. So for this one now, the p to q, you divide every one of the factors here by both of these in q. So I get plus minus 1 divided by plus minus 1 is the same. Plus minus 1 divided by plus minus 2 gives me plus minus 1 half. Now you try 2 at that. Plus minus 2 divided by plus minus 1 is plus minus 2. 2 by 2 is 1. I already have that one. We don't need to count it twice. Let's do 4. 4 divided by 1. So I get plus minus 4. And 4 divided by 2 is 2. I've already accounted for that one. Correct? So I don't need it. These are all possible rational zeros. Now, you can try among the list. I'm going to try negative 1/2 here on my list. Okay. And here's 2, negative 1, 7, negative 4, negative 4. Bring down the 2 and multiply. That gives me negative 1. 1 and 1, negative 2. The product is 1. 1 and 7, 8. Negative 1/2 times 8 is negative 4. Sum is negative 8. Negative 1/2 times negative 8 is 4. 4 and 4 is 0. Therefore, negative 1/2 is a solution. Okay, now, at this point, we have a third degree polynomial, and we could work this one again, rational zeros of this one. We have a list we can try out. And let's try 1. Let's try 1, see if that works. Bring down the 2, 1 by 2, 2, add 0, 1 times 0 is 0, add 1 times 8, 8, add. All the adds are in columns they appear in. Okay. So there you go, another 0 remainder. So that means 1 is a solution, and at this point I'm down to a quadratic, right? You start with x to the fourth, so the third row at this point, that polynomial is third degree. The new third row is going to be second degree. Now once we're down to a second degree again, you can continue on with rational zeros, or you can simply use quadratic formula. The quadratic we can solve. This is 2x squared plus 0x plus 8, if you will, which is just factor 2. It's just x squared plus 4. Now x squared plus 4, set it equal to 0. X squared is negative 4, so x would be plus minus square root of negative 4, which is 2i. So it does have two complex conjugate. Notice they're conjugates because the coefficients are real. So by conjugate pair theorem, we would expect 2 of them. And there we have the solution to this one. All right. And let's see, this is probably enough. Let's do one more. The more the merrier, right? Now let's try this last one. I promise this would be our last one. So this one, f of x, let's make it 5x cubed, negative 9x squared plus 28x plus 6. Now the rational zeros, again the ratio of p to q. P and q are plus minus 1, plus minus 2, plus minus 3, plus minus 6. These are all factors of 6, the constant. Factors of 5 plus minus 1 plus minus 5, because 5 is prime. In other words, here's what we're saying. Negative 1 times negative 5 is 5, so is 1 times 5. That's why we go both positive and negative factors in this case. Now for this one, I'm going to do the synthetic division, and our synthetic division, the first row is going to be 5, negative 9, 28, and 6. I'm going to try negative 1/5. I've tried it earlier and it worked. Remember, P over Q, by the way, is when you divide every one of these factors of P by each and every one of factors of Q. So plus minus, each and every one of the P divided by plus minus 1 gives you all of that list over again, right? That's divided by plus minus 1. Now divide by plus minus 5. So we're going to get plus minus 1/5, plus minus 2/5, plus minus 3/5, plus minus 6/5. So you see there's quite a few of these. If you want to go through the elimination process, try to narrow it down to specific zeros. But a whole bunch of them won't work, right? Because there's only 3 solutions in this one. It's a 3rd-degree polynomial. All right, let's bring down the 5 and process begins. Negative 1, that's negative 10. 10 times 1/5, 2. 2 and 28 makes 30. Negative 1/5, 30 is negative 6. Add, you get 0. And there you go. So this is going to work. So our factor is x minus makes x plus 1/5 times 5x squared, negative 10x plus 30. Now we want to find the zeros, right? So because I want to find the zeros for this one, I'm just going to solve this quadratic equation. Factor the 5 out, I get x squared minus 2x plus 6. And this one I'm going to use quadratic formula. Negative of b plus or minus b squared, that's 4, negative 2 squared, minus 4ac divided by 2 times a. That's going to be 2 plus or minus. The radicand is going to be 4 minus 24, which is negative 20. Square root of negative 20 divided by 2. That makes it 1 plus or minus. Square root of 20, that's 4 by 5, right? So that's 2 rad 5. This is plus or minus 2 root 5i divided by 2. I went ahead and divided 2 by 2, and that's how I got the 1. But you gotta also divide the radical by 2, the denominator. Perfect. So looks like the solution is going to be 1 plus or minus root 5i. There are 2 complex conjugate solutions in this one. So all in all, we have 3 solutions. The solutions you're looking at is x equal negative 1/5, the rational ones, and the 2 complex solutions. And that should do it. So again, it's a rather long section, but please watch it in segments, pieces, so you don't get too tired. And with that, we are done with this section, zeros of polynomial functions. Thank you for watching.